In our series devoted to information theory and math card magic, we now turn to the Gilbreath principle. This principle involves cyclic structures, and we will begin with the simplest of all cyclic structures, namely an alternating red-black packet of cards. And we'll be using Desmos to help us calculate surprisal values. So let's take a look at our activity here. Given a standard deck of 52 cards, we will analyze packets of size 2n that consist of n red cards and n black cards. To facilitate graphing in Desmos, the variable x will be used in place of n. In other words, the functional variable x that we will use represents the number of red cards, or black cards for that matter, in a packet consisting of an equal number of red and black cards. This means that the packet size of a given value of x is 2x. Since we are modeling possible scenarios for a deck of 52 cards, of which 26 are red and 26 are black, the permissible values of x are positive integers between 2 and 26 inclusive. Therefore, when interpreting the various graphs, we need to mentally double the value of each x-coordinate to obtain the actual size of the packet of cards being represented. Although each of the following functions only makes sense for discrete values of x, namely positive integers, Desmos uses a generalized factorial function, the gamma function, to draw a continuous graph that connects the corresponding discrete points in the plane. Surprisal analysis. To be able to understand the following surprisal functions, we'll need to do a little bit of analysis first. So let's take a look at the information I've written out on the right-hand side of the screen. So in this video, we're looking at cyclic structures having cycle length 2. For example, an alternating packet of red-black or black-red would be an example of this. So let's go ahead and declare the variable x as denoting the number of red cards in our packet. And that same value of x will denote the number of black cards, giving us a total of 2x cards. Now, the total number of alternating packets of red and black cards is the following. It's 2 times the quantity x factorial squared, where it is a positive integer between 2 and 26 inclusive. The total number of permutations of these 2x cards will, of course, be 2x factorial. The viewer, using just the fundamental counting principle from mathematics, also called the multiplication principle, can derive this expression right here. And it truly does give you the total number of alternating red-black packets, or black-red packets, where there are x red cards and x black cards. So I can leave that as an assignment for the viewer to verify. And I assure you, this is not a complicated derivation. So with the total number of what we call RB packets calculated, and the total number of permutations of this packet of 2x cards, we can calculate the probability that we would take a packet of cards in which there's an equal number of red and black, shuffle that, randomize it to our heart's content, and then find that that shuffled packet alternates perfectly in color. The probability of that happening is what we're going to find next. So given the above 2x cards, the probability that a random mixing of these cards would yield an alternating color packet is the following. It's the number of alternating color packets total divided by the total number of permutations of the cards in that packet. So this gives the probability that just by chance alone, we would mix those cards, display them, and find that they alternate in color. Now, you should not be surprised that the probability of that occurring by chance alone is very, very small. And as we will see, that is the case. Now, you may recall in our series, once you have the probability of an event, we can calculate the surprisal for that event. And that's found by simply calculating log base 2 of 1 divided by the probability of that event occurring. So here we obtain the following, log base 2 of this quantity here, where once again, x is between 2 and 26 inclusive. So let's go ahead and take a look at our Desmos activity, where these computations are performed for us. So right now we will focus on the top Surprisal function, and that's the one that we've just derived here. So once again, the values of x are denoting the number of red cards and separately the number of black cards. So to get the total packet size, we have to double the value of x listed. So where we see a 2 here, we're looking at a packet that has 2 red cards and 2 black cards. So the total packet size is 4. And the surprisal associated with that packet of 4 cards, in which 2 are red and 2 are black, the surprisal associated with just mixing those 4 cards, laying them out, and finding that they alternate in color is 1.58 bits. So it's a little more likely than tossing a single fair coin, calling heads, and having it land heads up. The surprisal associated with that outcome is 1 bit. And I suppose I should quickly remind you of our interpretation of surprisal values. If we just focus on the whole number portion of these values, we get a 1, 3, 5, 6, 8, 10, and so forth. The interpretation for each of those is they correspond to a surprisal value that can be interpreted in terms of ordinary coin tosses. So for example, if we have 12 red cards and 12 black cards and mix them and lay them out and find that they alternate in color, the surprisal value for that outcome would be over 20 bits of surprisal. How do we interpret 20 bits? 20 bits is the same level of surprise associated with tossing 20 fair coins high up into the air and calling heads for all of them, and then watching those coins hit the table and bounce and eventually settle down, and all 20 coins are heads up. The level of surprise associated with that outcome is the same level of surprise associated with having 12 red cards and 12 black cards, mixing them randomly, laying them out, and finding that they alternate red, black, or possibly black, red throughout. Okay, so that gives you an idea as to how unlikely or how surprising that outcome would be. Now, in some ways, we shouldn't be all that surprised that randomly mixing an equal portion of red and black cards, coming out to be a perfect alternation in colors, is highly unlikely, leading to a very high surprisal value. That, in and of itself, would really not surprise anyone. But the Gilbreath principle allows us to do something amazing with the cards that involves randomly dealing out a portion of the packet and then riffle shuffling them together in a haphazard and messy fashion, and nonetheless, the ending packet has a structure that leads to a very high surprisal value. And we know this because of the Gilbreath principle. So let's go ahead and just demonstrate that. So here I have the entire deck set up as red, black throughout. This is alternating in color, as is. Sorry, you can't quite see it all, but you'll just have to trust that that's the case. These are all alternating in color, okay? So for this to happen by chance alone, by the way, let's go ahead and just look at our Desmos activity here. If we go to the bottom, what do we see for 26 red cards and 26 black cards, which is what we're looking at right here? What are the chances that you would just mix these cards randomly, display them, and find that they perfectly alternate in color? Well, as we can see on the table there, the surprisal associated with that outcome is 47.81 bits. Well, to give you a frame of reference, the surprisal associated with winning most any lottery out there, or the surprisal for being struck by lightning, is about 20 bits. So this 47 bits is more than double that. So that would be like winning a high stakes lottery twice or being struck by lightning twice. Okay? Very, very unlikely. Now, once again, we're not surprised that it would be unlikely. Think about it. If these were randomly mixed and shuffled, what are the chances that they would alternate in color when we're finished with our, quote, randomization of the packet? Very, very small. So essentially, that's where we're beginning with a Gilbreath performance involving cyclic packets having cycle length 2. So what we do now to make use of the powerful Gilbreath principle is we start with a cyclic construction of the deck in some way, and this one is an alternating red-black organization of the cards, and the Gilbreath principle says the following: we can deal out as many cards as we like to the table. The spectator can decide this. So you can deal until they say stop, okay? And it would be nice to get about half, but you don't have to. They can stop at any point. Maybe they say stop there. That's just fine, okay? So we've dealt out a number of cards to the table. From this point, we can riffle shuffle the cards together. A riffle shuffle is where you have a deck. You kind of split it, well, roughly in half, I guess, and then just let the cards fall left, right, how they may. That's a riffle shuffle. Okay. Now, another shuffle that's equivalent to it is called the rosette shuffle. This is where you just spin the cards and then just bring them together. That is equivalent to a riffle shuffle. And so this will accomplish the same thing that a riffle shuffle would have accomplished. Okay. And what that means then is the Gilbreath principle applies to this packet now. If I can pick it up. Okay, so just think about how haphazardly those cards interlaced. In fact, you can kind of see here. I mean, they're all over the place, right? Okay, no one's controlling that at all, okay? Nonetheless, the Gilbreath principle says something amazing about the ending structure. What does it say? Do you remember? It says that now if you take off pairs of cards, in other words, a number of cards that equals the cycle length, each pair of cards will consist of a black card and a red card in some order. Okay, so we have black, red, black, red, black, red, black, red, black, red, red, black. We finally got a red, black. Hooray! Red, black, black, red, red, black. The key is there's one of each. Red, black, black, red, black, red, black, red, black, red, red, black, black, red, black, red, red, black, red, black, red, black. Amazing. Red, black, red, black, red, black, black, red, black, red, and finally black, red. Each pair is guaranteed to consist of one of each color. Now, it is true we don't know the order, okay? And that's asking for too much. We would need something much stronger than the Gilbreath principle, but the fact is you would not be able to do the mixing that I've just done, where I reverse counted cards to the table and then I did this rosette shuffle. The Gilbreath principle tells us as much as we can know about the ending structure, and the fact that it has any consistent, predictable structure is amazing, considering that the number of cards dealt out is random and they are just randomly interlacing themselves in some way. Okay, absolutely amazing. So that's just an application of the Gilbreath principle. And knowing this much about the ending structure, if you look to other places on my channel, there are just countless really fun, surprising, engaging routines that are based on the Gilbreath principle. Okay, but here, right now, our focus is on calculating surprisal values for Gilbreath performances. So, we know that the surprisal value associated with just randomly mixing a standard deck and finding that the cards are perfectly alternated in color is through the roof, 47 bits. Okay, now let's look at a post-Gilbreath surprisal function. Okay, and so that's what the second function is here, called S sub. Instead of RB for RB packets, it says GRB. Among the hidden structures online class videos, I derived not only the first one that we've been using, but I also derived the one for the post-Gilbreath structure, namely this one here. Okay, and you can see just small differences between these two expressions inside the parentheses. Okay, but this will truly give you the total number of ways that you can have a packet of cards where you have an equal portion of red and black, and then arrange them so that every pair of cards taken from the top consists of a red and a black in some order, in any order, actually. Okay? Now, for the purists out there, those who really know their stuff, I should point out a subtlety here that is pretty amazing to contemplate. So what I'm going to point out here is in the derivation of this expression, what this actually finds for us is all of the ways in which an equal portion of red and black cards could be so arranged so that when taken as pairs from the top, each pair consists of a red or black. That's what this is calculating here. Okay? Now, it's probably the correct calculation to use when determining the surprisal for the outcome of this Gilbreath routine in the minds of the spectators. Okay? But I do want to point out that technically speaking, the true surprisal values for a post-Gilbreath packet is higher than what is being calculated here or in the table down below. But I believe the values I've listed here are truer to what the spectator is perceiving the likelihood of this outcome to be, meaning the surprisal values listed on my table are more accurate than necessarily calculating the precise probability of achieving a post-Gilbreath structure from an alternating color packet. Okay? All of that said, what I'm stating is that these are conservative. If anything, the surprisal values for the middle column here in reality are higher than those listed. Yet I think the ones I've listed are closer to what the spectator would actually experience in watching this routine. Okay, so let's take a look then. I had the entire deck set up as red, black throughout. I performed a Gilbreath shuffle. it resulted in a packet that has the property that as you take pairs of cards from the top, each pair consists of a red card and a black card in some order. The Surprisal value associated with doing what we just did here, given that we ostensibly randomize the cards when we mix them, the Surprisal value is just short of 23 bits. Okay? So, we can immediately interpret the Surprisal value of this Gilbreath performance as being the same level of surprise associated with being struck by lightning. Okay? Another interpretation that we gave for Surprisal values, we can go ahead and just round this to 23 bits, would be the level of surprise in observing this outcome is the same level of surprise one would experience in taking a true-false 23-question quiz, closing your eyes, and just guessing either true or false for every one of those questions. And then, in the end, when that quiz is graded, you aced it. Every one of your guesses was correct. All 23 random guesses for either true or false for those 23 questions were right. You aced the exam despite just randomly listing T's or F's as you work down that quiz. Okay? So that's another interpretation of the level of surprise associated with this Gilbreath performance here. Okay? So very, very surprising. In fact, let's go ahead and take a look at the graphs since we've gone through the trouble of creating these Surprisal functions. So here's the one for the original packet structure that we started with, where the cards alternated in color. Now remember, the x values down here have to be doubled to actually obtain the true packet size. So for example, you can see the 10 here. Well, that's representing 10 red cards and 10 black cards. So the total packet size is 20. And so the level of surprise associated with just mixing those 20 cards and finding that they alternate in color perfectly is about 16, 17 bits of Surprisal. And of course, we can get the exact value or near exact value over here in the chart. Here's 10. Surprisal value for the original, quote, RB packet is 16.49 bits. And then if we were to Gilbreath shuffle that packet, the ending structure would generate about 7.5 bits of Surprisal, because every pair of cards taken from the top will consist of one red and one black. And that can be seen on the second graph here, the green one, okay? So the blue one is for the original perfectly alternating color packet, and the green one is for the Gilbreath shuffled packet that has that special property that, taken as pairs, each pair consists of exactly one red and one black. You'll never get two blacks, or you'll never get two reds. You'll always get one of each if you take off pairs starting from the top. And then I also have here the difference in Surprisal values. So it's just showing you the difference in the Surprisal values between these two Surprisal functions. And then down here, if we click, we'll get the true values x can take on, because x needs to be a positive integer between 2 and 26. And as mentioned earlier, Desmos is connecting them using the gamma function. Okay, so technically it's only the dots that exist in the card performances that we're looking at. Okay, but it's kind of nice to see them connected to get an overall picture of whatever pattern we're looking at. I suppose another way to use this Desmos activity is to decide on what Surprisal value would you like to achieve, starting with an alternating color packet. Kind of an interesting question. So for example, if you're wanting to achieve about 10 bits of Surprisal, okay, that would be like tossing 10 fair coins into the air calling heads on all of them, and then watching those coins land heads up. Each and every one of the 10 coins is heads up. So if you would like to create a performance of that level of surprise, 10 bits, which is extremely surprising, what you would need to do is just grab a deck of cards. And so we can quickly just do this to finish up here. And so look off to the left, the X value on the left-hand side of the table that corresponds to a Gilbreath performance having a Surprisal of about 10 bits. So come over here. So what is the case then is if we have 13 red cards and 13 black cards that begin as perfectly alternating. So let's do that first. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's just check that. So I just have 13, or at least I should have 13 red cards, 13 black cards, and I'm hoping that they alternate perfectly in color. Okay, that's the goal here. Okay, do they alternate in color? Well, we'll find out here. Okay, so what do we find here? Well, let's see. Red, black, 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 red, black. Okay, perfect. Okay, so we begin with this. You always need a cyclic packet in order to apply the Gilbreath principle. And now we're free to perform a Gilbreath shuffle. Okay. Now, as I've mentioned, the standard way is to deal out a number of cards until the spectator says stop, and then riffle shuffle or rosette shuffle those together. Now, another shuffle that's equivalent to a Gilbreath shuffle is the following, which is a fun one to do as well. And if you give it a little bit of thought and analysis, you'll realize that this is equivalent to a Gilbreath shuffle. So what does this involve? This involves asking the spectator, should you draw from the top or the bottom as you set cards on the table? And they can draw from the top or bottom more than once. Okay? So maybe they'll say top, and they'll say bottom, bottom, top, bottom, and maybe they'll say top, 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 then bottom, top, bottom, bottom, top, top, bottom, 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 bottom. Wow. Top, bottom, top, bottom, top, top, bottom, bottom. Okay? Now, as you can check, that's equivalent to have dealt out a certain number of cards and riffle shuffling those cards together. In other words, it's a Gilbreath shuffle. Okay? It's called an in-hand Gilbreath shuffle. Okay? Well, what does that mean? That means the Gilbreath principle applies because we had a cyclic structure that alternated in color. We performed a Gilbreath shuffle. Now the Gilbreath principle guarantees the following. If we look at groups of cards that equal the cycle length of the original cyclic packet, namely 2, each pair taken from the top will consist of 1 red and 1 black in some order. Okay? So, and then if we're successful in doing that, what we've shown on the chart is that we will be achieving 10 bits of Surprisal. So that goes back to what we said about, let's say, coin tosses. The surprise associated with what we'll see next here is the same as tossing 10 coins high up into the air, telling the spectator they're all going to land heads up. And they're going to look at you like, yeah, right. And then the coins land and bounce and eventually settle down. And each and every one of the 10 coins is heads up. and then you'll just watch the spectator's eyes go big if they don't pass out or something, okay? So let's see if we achieve that same level of surprise by demonstrating that every pair of cards taken from the top consists of a red and a black in some order. So we have red, black, black, red, red, black, black, red, red, black, red, black, black, red, red, black, black, red, red, black, red, black, black, red, and finally black, red. We nailed it. The probability of this happening by chance alone is extremely small, which is why it leads to a surprisal value of over 10 bits, as listed here, okay? So that's why if you perform this and use one of the narratives for revealing this outcome in a fun and creative way, you'll get such a strong positive reaction from the spectator as they try to figure out how in the world is that even possible given the random choices they were making and having you draw from the top or the bottom more than once if they liked. They decided all of that, and despite those choices, you still ended in the way that you intended to end. Namely, every pair of cards taken from the top consists of one red and one black in some order. Okay, so this is our first video dedicated to calculating surprisal values for Gilbreath performances. Next time, we will look at cyclic structures having cycle length 4 instead of 2. And as you might imagine, the surprisal values will jump even higher. Okay, so thank you for watching, and join me in the next video dedicated to information theory and math card magic.